So I just heard I'm going to do this in English, which means I got about halfway translating my slides, so sorry about that. Yeah, I'm going to do a quick talk, well, like 45 minutes, I believe, something like that, about Wi-Fi 7 and everything that's going to be in it, and maybe not, because it's still not a standard. So I'm going to overload you with a lot of information. I'm sure we're going to share the slides afterwards. I'm looking for Arjan, I don't know where he is. So you don't have to remember everything. It would be a very accomplishing, a very big accomplishment if you could remember everything, because we're going to talk about a lot. So I'm going to do a quick introduction of myself. I'm going to keep it very short. I'm going to tell you everything, or at least everything that I could find, or at least found interesting enough to put in the slides about Wi-Fi 7, but we're also at the end going to talk a little bit into the future, look into the future about what Wi-Fi next standard maybe will have in it, and also a very little bit about 6G, because that's coming as well. Mark, are we going to share the slides afterwards?
Yes.
Okay, well, you're going to get a translated one by then. I'll send an extra, so who am I? For those of you who don't know me, this should be introduction. You see I missed a couple of things. I'm a wireless consultant, CWNE number 325. I've been doing Wi-Fi since it wasn't called Wi-Fi, which is back in '98. I was introduced into something called No Wires Needed. Anybody heard of that? I see a couple of nods. Yeah, you do. Of course you do. Which was a Dutch product that did 802.11. No letters, just .11. And it was called wireless. It wasn't called Wi-Fi back then. So that's where I started with wireless, which is very cool. A couple of projects that I do, that I did. Big drilling platform, I do some lectures, did a lot of high density stuff, cool stuff. Anyway, that's me. That's not what we're going to talk about. We're going to talk about it. So I edited the Wi-Fi 6 logo because there's no Wi-Fi 7 logo yet. Why? Because it's not certified yet. The WLA is currently, or the WFA, sorry, is currently working on its certification program, which will be released by the end of this year, or somewhere around 3/4 of this year. And by then, products are going to be tested and certified. So it's not yet certified. So this logo is as illegal as you can get it. But yay to Photoshop. So what is it? Well, Wi-Fi 7 basically is the true standard is 802.11be. And it's got a couple of goals defined. Before they started actually building the standard, they had a couple of goals with the three top ones being low latency, meaning I want something like less than 5 milliseconds latency performance. I want to have a high throughput and a high data rate. What else is new in a new standard in Wi-Fi? Except 11AX, but that has it as well. And I want less jitter. Missed that one as well. You're going to see a lot more. So those were the three top goals they had with regards to the new standard. They also said, well, we want to do like something like 4 times upgrade with regards to 11AX, meaning we're going to do something like 4K QAM, 16 spatial streams, yeah, right. And 320 megahertz channels. Well, yeah, true, not in the UK, in the UE, in the EU, sorry. But we'll get to that a bit later. So these were the main goals they set out when the task group was formed to initiate the Wi-Fi 7 standard. The one thing that I didn't mention here is, and I'm going to get back to that a bit later, is, and I want to have a drum roll here, is this one. I don't know if you heard of it, but it's MLO, meaning multi-link operation. So this is a teaser. I'm going to get back to that. But this is most likely going to be the big hit within Wi-Fi 7. I suspect that most vendors will push on this, especially from the client side. Maybe not so much from the enterprise side, so from the access point perhaps as well, but specifically from the client side. And I'll get back to it, what MLO actually means for you. It is interesting. But first back to the timeline, because they started out like in 2019, I believe. I have a timeline later on. But the plan is to be 6 months quicker than the release of 11AX, which was already a pretty fast upgrade after 11AC. But they plan to do it half a year faster than 11AX, meaning that the first enterprise products are expected in next year, early next year, halfway next year. I'm not a vendor, so I have no insights in the actual development of hardware from that side. But they expect consumer products to hit the market by the end of this year. Actually, there are already a couple of consumer products out there, which are, again, not certified, but it's there already. So it's going really fast. Like in 11AC, if you remember that, you had wave 1 and wave 2. They're planning the same thing, kind of the same thing with Wi-Fi 7, but they're going to call it release 1 and release 2. So release 1 is going to have mostly PHY changes, so that's where the hardware changes are going to be. And they plan to have release 2 products somewhere in 2025, which most likely will only have MAC changes. So hopefully that's going to be software only, but I have no insights in that yet. And the reason is they want to push new PHY updates to a next release in order to keep the market going, to not over-aggress the market in developing new hardware and stuff like that. So that's the plan. And we'll see how that turns out, but that's the idea they have. If you look at the timeline, we've got an approval in March 2019. That's where they actually started to agree on some of the goals and the fact that they're going to develop a new standard. A lot has happened in the meantime, and we're now in almost draft 4.0. I haven't checked the IEEE site yet, so I'm not sure if it's already there. Usually they lag a bit, so it's probably going to be a little bit later than May. So we're now between draft 3.0 and draft 4.0. The thing is, products are already there. So silicon vendors, Broadcom, Qualcomm, and all those guys, already started developing their silicon back in 2021. And we're now about to go into the phase where the actual hardware is going to hit market. There are some videos out there on YouTube from Intel and stuff like that that show you massive bandwidth using Wi-Fi 7, meaning that that hardware is already available at the vendor, and it's going to hit the market pretty soon. And somewhere around here, we're going to get the Wi-Fi alignment certification with the expected approval somewhere in March 2024. But most likely that will be extended a little bit, but we'll see. So this is where we're at the moment. Again, the release 2 is planned to be lightweight, meaning that most features that you're going to see will be in release 1, but a lot may also venture into the next Wi-Fi standard. I know it's a bit vague, but that's where we are at the moment. So what are the features that they, well, a lot of features that they thought of for Wi-Fi 7? Well, here's a list, and yes, we're going to go through all of them, so bear with me. First of all, the acronym that they're going to use is EHT, extremely high throughput. So you have high throughput, you have high efficiency, very high throughput, and now we've got extremely high throughput. Makes me wonder what the next release is going to be. Ridiculous throughput or ludicrous throughput or whatever they're going to come up with. This is what they're going to call it right now. It's EHT, extremely high throughput. I like the ludicrous high throughput, LHT. They're planning to be backwards compatible through all 3 bands, which is good news. Although 2.4 is probably dead for your normal communication, but for the IoT kind of space and long distance things, it might be interesting. Again, 320 MHz for non-EU, 4K-PON, LMO, MLO. We're going to talk about multi-AP coordination, which is very interesting, but also very complex. So I doubt if this is going to be part of the first release or even the second release. This is something you probably never heard of, but are using slightly different a lot. So I'll mention that briefly. preamble puncturing, something that's already in AX that's being extended, spatial streams. We're going to go through them. First of all, extremely high throughput. So, like I mentioned, almost every standard has higher bandwidth specifications in it. Nothing different in Wi-Fi 7. But if you look at the history of Wi-Fi, when we were at 11N, the jump to Wi-Fi 5, so 11AC, was focused solely on bandwidth. That was the thing at the moment. You needed more bandwidth. You wanted more bandwidth. Everybody needed more bandwidth. And suddenly there were a lot of devices that want to access the network that didn't need all that bandwidth. So the 11AX had in mind a more efficiency focus rather than a bandwidth focus. That's where 11AX got its name from. It's more suited for more efficient use of the Wi-Fi and more clients being connected to the Wi-Fi rather than having these ludicrous high bandwidth requirements. And then they thought of Wi-Fi 7. Well, what are we going to do with Wi-Fi 7? Well, basically they said we're going to do everything. We're going to do more efficient use of the spectrum. We're going to use higher bandwidth if possible, with a goal. And these are not my thing, but these are marketing numbers. And I just copied them out of the standard. So if you look at the maximum speed with with the 16 spatial streams at 11 BE, you're going to look at 46.6 gigabits per second.
Yeah.
You are never going to get 46.6 gigabits per second through the air. This is what the chipset should be able to process internally. This is never going through the air. Sorry?
Fantasyland.
Fantasyland, yeah, absolutely. But these are the numbers you need to look out for, because these are the numbers that some vendors will post, especially in marketing slides. But keep in mind, this is what's happening, or could happen internally in the chip. So that's where the chip designers should focus on. You're never going to see this go, not even in a lab situation. Not going to happen. And again, this requires 16 spatial streams. Well, let's find a client with 16 spatial streams first. Anyway, again, extremely high throughput. They're going to design, or they have designed, a new PPU. Now, without going into details how PPUs, PSUs, and all that stuff work, basically what it means is, in the past, prior to Wi-Fi 7, every new standard added a bit of data to a frame, to a preamble frame within Wi-Fi. So this preamble was getting bigger and bigger and bigger and creating more overhead than you wanted. And again, one of the goals of Wi-Fi 7 is to reduce overhead, or basically enhance the latency and efficiency. So what they did is they designed a universal signaling field. So instead of, well, they did add a new field, but instead of adding a new field specifically for this standard only, they've now added a signaling field that's universal with forward compatibility in mind. Meaning that the next standard should use the same field, just with another setting of bits, instead of adding another field. They're going to use the same universal signaling field. So it's 2 symbols per 20 megahertz, so there's room there for different options. That's the idea, forward compatibility. We're still going to be left with all the legacy stuff from the past, which also means 11AX and 11AC and 11N and everything else. But this is the first step into a more efficient use of the spectrum, besides all the other stuff that came in 11AX. So keep your eye on that, out for that. And yeah, forward compatibility. So you're looking at Wi-Fi 8, Wi-Fi 9, Wi-Fi 10. That's not happening. Maybe 11, but I'll probably be out of work by then. Anyway, so that's the extremely high throughput. The other thing is the spectrum. So there, we all know, hopefully, that we got the 6 gigahertz band added to our Wi-Fi domain, and only the UNII 5 for the EU. They planned 320 megahertz use in Wi-Fi 7. That's great if you're in the US or something in the A regulatory domain, where you have the 1200 megahertz bandwidth available to you. Meaning that if you look at the bottom, you've got 1, 2, 3 separate 320 megahertz channels. So even in an enterprise environment where you can use the entire 1200 megahertz of bandwidth, you still have only 320 megahertz channels. But in a small environment, home environment, something like that, that could be interesting. That's not going to fly in the EU. Because we only have this little 500 megahertz block, meaning that we've got one non-overlapping 320 megahertz channel. I doubt that it's even going to be enabled in the enterprise products, maybe in the consumer products. So at home you might be able to run 320 megahertz, not sure, we're going to see. Most likely you're going to see a lot of 40 and maybe even 80 megahertz channels if you're going to deploy Wi-Fi 6 or Wi-Fi 7 in the enterprise. Because even with 80 megahertz, you're looking at 1, 2, 3, 4, 5, 6 separate channels, which will be doable. 160 megahertz, you've got only 3. Again, probably not going to happen if you're designing your network correctly. But this is what you've got. In order to get those extremely high throughput bandwidths, they designed something called 4K QAM. Now, QAM is not new. It was introduced in 11N, where you've got 16 QAM, 64 QAM. Back in AX, you've got 1024, so 1K QAM. And now we're at 4K QAM. So 4069 different positions within a constellation. This is what's called a QI constellation, where you can modulate 12 bits per symbol. So each and every dot represents 12 unique bits. That's really cool, and that's going to give you an extremely high bandwidth. But it also requires an enormously high signal-to-noise ratio. And the reason being, I always imagine if I have to explain how this works, I always also explain this as being like a dartboard. And you want to hit the bullseye, every red dot is the bullseye, very accurately. Now I've seen a couple of those dart competitions, that's hard. That's even harder if these points are really close to each other. And that's where this point, this diagram comes into play. This is what's called a error vector magnitude representation. So what this means is, if this is my actual location of one of those dots, so representing 12 bits, the deviation that I'm allowed to have is very small. So the angle and the amplitude is very small compared to where I should be. Meaning that if you translate that into actual numbers, the EVM for this 4K QAM is minus 38 dB. Now you probably haven't heard about EVM before. You most likely have heard about SNR, signal-to-noise ratio. There is a formula depending on the type of QAM you're using to translate EVM translate EVM into SNR. Basically, if you're looking at a high QAM rate, it's about 3 to 4 dBm stronger in SNR that you require. So in case of 4K QAM in 11BE, where I require minus 38 dB for EVM, if you recalculate that, it's going to come to like minus 40, 41 SNR, oh no, not minus, but SNR 40, 41, 42 dB. If you translate that into real life situations, you're going to sit on top of your AP to actually reach that number. Depending on your client, but getting a SNR of 40 or higher is like, if I have to have, if I want to get that coverage here in this room, I'll probably need an AP around every 2 or 3 meters. So this is not realistic. This is only realistic in a testing environment and maybe in some very unique situations. You're not gonna let me put it differently. If this is one of your requirements for a complete network, you've got a challenge or a lot of budget. Yeah, I'm all for it. You are.
Maybe 2 meters, maybe. Or just jack the wire, stick it down. Probably works better.
So just a little bit on how EVM works and how this relates to SNR. So remove the minus, add about 2 to 3 dB for a higher QAM rate, and you've got about the SNR you require to have in order to get these modulation times.
So is this only marketing? I mean, the spawn rates are so high you can't reach them in real life. I mean, I'm not getting the 265. Occasionally, when you're under the IP, so what's the purpose of such a high spawn rate?
Primarily, I haven't been in the task group to actually think about this, but if I think about real life scenarios, you could think about point-to-point connections with highly directional antennas.
Yep.
There are some use cases where you could actually use this. If you can't reach a cable drop somewhere, you could do like a mesh kind of thing, again point-to-point. It's just not, in my opinion, not usable for clients in real scenarios, especially in high density, but there could be use cases where you might want this. Maybe you remember in one of the first slides where the overview was, I put in a little picture of a cable with a scissor, cutting the cable. It could be a use case for a all wireless solution, and we already do a lot of all wireless solutions in offices and stuff like that, but you have certain use cases like where you require high bandwidth for CAD drawings, for instance. Where you can put like an AP near to the client and actually reach these kind of speeds and these kind of modulations for that specific use case. But again, do not try and write like a request for or an RFP or whatever for a full coverage on 4K QAM. And in the past we've seen these kind of requirements in RFPs that are completely idiotic, but this is specifically for some very specific use cases.
Okay.
But it is possible. I mean, the technology is there to reach these kind of communications. The source of this is, if you want to have like deep information about this kind of stuff, look at LightPoint. LightPoint builds testing equipment for vendors like Qualcomm and Broadcom and stuff like that to actually make this possible and measure this and see how well this works in a real life environment and if that chipset actually functions the way they are designed to function. Yeah, so that's QAM. MLO, multi-link operation. It's a completely new idea in Wi-Fi. And the idea is to have a more efficient use of multiple bands, because now, up until now, you could either use 2.4 or 5 or 6 with 16, but never a combination of those. You could roam between, you could move between those bands, but you couldn't use them at the same time. The idea of MLO is to have multiple modes where you could do, well, something like, it's kind of a dirty word in Wi-Fi, full duplex. It's not really full duplex because you're using different bands, but you're transmitting and receiving at the same time, which is basically full duplex, depending on how you're going to use it. So they came up with two modes, MLO, simultaneous transmission reception, and non-simultaneous transmission. Now I'm going to explain a bit what this means because there's a lot of text and it's not really clear. So if you look at an example or three examples, first example is I can use, for instance, the 5 gigahertz link for receiving data and use the 6 gigahertz link for transmitting data. Or I could use 5 and 6 gigahertz both at the same time for receiving data or for transmitting data. Now this poses a lot of challenges, like channel usage or channel availability. I have to check whether the channel is available to me or not, and I have to do this on both 5 and 6 or 2.4 and 5 or whatever combination you're thinking of. So which is going to be first? If you do that with separated downlink and uplink data, then you're probably going to be most successful, because these are two different modes, two different usages of the link. Whereas if you want to download or upload on both the links at the same time, which is going to be first? 5 gigahertz most likely is going to be more utilized than 6 gigahertz, simply because it's been there longer. So the chances that 5 gigahertz is going to be available at the same time as 6 gigahertz is slim. So how are you going to deal with that? It's a lot of challenges. The other challenge, I think I've got something here as well. No, not. So the other challenge is, what about the power that I'm using to transmit from a client or an access point of view? What about the, if I have a high 5 gigahertz channel and a low 6 gigahertz channel, they're really close to each other. So what about the harmonization between those different bands? And what is that going to do to my electronics, so my actual chipset on board, the AP or the client? So a lot of challenges that need to be solved in order for this to work. But I suspect this is one of the things that's coming in the first release of Wi-Fi 7. Other thing that's kind of related to that, so again, higher efficiency, more bandwidth and stuff like that, is multi-AP coordination. The chances are that this is going to be moved into the next 11.11 release and not going to be available in the Wi-Fi 7 release, but we'll wait and see. In a short overview, and I have no idea how I'm doing on time, but I don't really care.
5 minutes left.
Yeah. So multi-AP has the idea of doing something more interesting with beamforming, jump transmission, and the OFDMA design that already was introduced in 11AX. So rather than reading out all this stuff, I'm going to again show you a couple of examples. So from the 3 different modes that they have come up with, the first one is coordinated OFDMA, or more explanatory spatial reuse, which basically means that in this case 2 access points are going to communicate to each other, saying that, hey, I'm going to transmit to this station, you're probably going to transmit to that station, expecting them to be on the same channel, which is why this is designed. I'm going to tell the APs among each other to either lower or increase the power in order to minimize channel overlap. That's the idea. So this requires an enormous coordination between the 2 access points and a lot of data sharing what the access point has learned about the client. But that's the first use case. The second use case is, and this is one of the reasons that those multiple spatial streams might come in handy, especially in the access points, which is easier to build in access points than it is in clients. And that's null steering or coordinated beamforming, which basically means that if I can use 1 or 2 or a couple of antennas in the access point to steer, to generate null data, so null signals, the exact opposite of what I'm trying to reach, is that I can create like a dead zone, so a shadowing zone between the stations in order to minimize co-channel interference again. So again, that requires very high coordination between the 2 access points, and it's going to be very complex. Most likely, if at all, it's going to be part of Wi-Fi 7, is the jump transmission, where we can distribute the data that has to go to the station between multiple access points and have them transmitted to the client, maybe using 2 different bands, in order to get a higher throughput or a higher efficiency. So again, the reliability might be one of the better use cases, not so much the bandwidth, because I could send 2 different packets at the same time, doubling my speed basically, or I can duplicate the packet, creating a situation where the chances that that packet is going to arrive at the client is going to be much higher than when I only transmit it over one link. So that's more like a reliability feature rather than a high bandwidth feature. This is, well, I'm telling you it's easier to accomplish. I would have no idea how to do it, but this is most likely the one that's going to be there. I hope. So that is multi-AP. Then I mentioned HARQ, H-A-R-Q, like you already use this but in a different way, but you probably never knew it. Without going through, this is the point where I didn't have enough time to translate everything. I'm sorry. Anyway, without going through all the text, what it basically means, what Wi-Fi does at the moment, so prior to Wi-Fi 7, is if you send a frame and the frame is corrupted in any way, it's going to be discarded entirely. You just have to resend the entire frame because the client, if you look at the client side at least, is not going to keep it. But what if there's a bit of that packet that's still perfectly fine, it's just a small part of that packet that's corrupted. I'm going to discard everything that's good and bad, and the bad part isn't that problem. The good part is, why do I discard that? What if I keep that and then resend the packet that might be corrupted as well, but maybe another part is corrupted? And if I combine those two, then I've got a good packet. That's the idea behind hybrid ARP. Again, this is not going to help you gain high throughput or whatever, but if you have a very noisy environment, very high utilization, a lot of frames that are being corrupted, this might help you to at least get something more efficient and more reliable to the client. So in a very noisy environment, this might help you. Hybrid ARP. What is my time, Mark? Actually, I have no idea. 10 o'clock? 30. Okay, I'm good. Other feature, preamble puncturing, was already introduced in 11AX with an option for the client to actually use that. The thing is, it was only for multiple users in an OFDMA environment. And you don't see a lot of OFDMA. You have to have like all clients that support that in order to efficiently use OFDMA and multiple users. In Wi-Fi 7, they are opting for single user and non-OFDMA, so OFDM clients. Where I can, if I have like a jammed channel in a 4x20 bundle, instead of dropping back to 20 megahertz, I can now just skip that channel for single users, for instance, and still have like 60 megahertz available for transmission. Again, more efficient. Instead of dropping a lot of channels, going back to 20 megahertz, I now can do like 20, 40, 60, instead of 80 only, 20 or 80 only. That's the idea of preamble puncturing in a new way. Hard to measure, I think. I've never looked into it, how this works in real life, but the idea is good and more efficient. So preamble puncturing. Then I mentioned spatial streams, where they are planning to go from 8 spatial streams in 11AX to 16 in Wi-Fi 7, so 11BE. I haven't even seen an 8-stream 11AX AP in all this time, so I'm very reluctant in seeing a 16-stream device in Wi-Fi 7, but the standard supports it. Again, this might be interesting, and I wouldn't even start imagining how an access point would look like with 16 radio channels. But okay, it's interesting. It might be interesting for multiple users, for this spatial coordination, for point-to-point links and stuff like that, because it's not necessarily that you have to have a client with 16 streams as well. As you can see here, if I have a client with 2 spatial stream support, which are most clients anyway, most laptops, and maybe a couple with 4, again with 2, here a couple, again a couple with 4, and a couple with 4, I could very optimal make use of my access point if my access point would support this, and if my clients would support this. However, you also need a lot of spatial diversion, meaning that the clients need to be separated physically well enough in order to do this, in order to minimize the channel overlap or the beam overlap. So real life scenarios will probably never show you this, but again, this is the standard and that's what you see in a lot of standards. It is possible. In real life, you're going to see less of these kind of situations. Not to mention how to troubleshoot it, that's another thing. Then there is also something in 11AX that was introduced, which are called resource units, where we could split a 20 megahertz channel, 40 or 80 megahertz for that matter, into multiple smaller groups. In 11AX, this was done purely for efficiency, so more efficient use of the 20 meg of a channel, no matter what size the channel. But it was only efficient if you had like a even number of clients, so either 2, 4, 6, 8 or 16 users, where we could evenly distribute those different resource units into blocks that were equal. In real life, you never have that situation. You hope you have that situation, but reality kicks in and you got either 3 or 7 or 5 clients, it's always the case. Something with Murphy or something. So any uneven number of clients, this was started to become less efficient. So what they came up with in Wi-Fi 7 is instead of doing these equal blocks or what's called we can, where you can only address a block of resource units to one client, Wi-Fi 7 now says, well, what if I have a client with very low bandwidth requirements, but I'm just going to give them like a small block of resource units, and I've got this big bandwidth user, and I'm going to give them all the remaining blocks. This was not possible in 11AX. This will be possible in 11BE. Or if I have 2 different users with slightly more bandwidth than a single one, and even more bandwidth usage for a second user, I can again combine these. More efficient use of the spectrum. That's the idea. This means something for the number of data rates you are going to be presented with. And back in 11N, I believe, the introduction was done of MCS rates, so you should be familiar with them by now. Modulation coding schemes. There's this nice slide, and again, you're going to get the slide, so no worry, you don't have to memorize this. This shows you the entire table of all the MCS rates up to 11AX. It hasn't been updated to 11BE yet, simply because the standard isn't there yet. But this is the screenshot of the entire table for up to 11AX, and the small takeout is this. So you've got the different high throughput, very high throughput, high efficiency, or there's going to be extremely high throughput added here. Then you've got the different spatial streams, which is going to be double. You've got the modulation that's going to be 4 times bigger than the biggest one at the moment. But you can imagine what this does to this table. Luckily, you don't have to memorize all the speeds anymore like you used to do in 11B and G and stuff like that. Those were easy. That's impossible now. If you can memorize this, then I bow to you. But this is impossible. So even in the highest possible scenario in 11AX with 160 megahertz channel at the smallest guard interval, you are looking at more than 9 gigabits per second data rate on throughput. So this is everything perfectly with all the possibilities you have in 11AX. And that's where you're going to see this 46.6 gigabits per second show up in the table. Again, you're never going to see it in real life because you're also never going to see 9.6 gigabits per second in real life, and that's there now. I haven't seen it, but that's what the table represents. Now the design or the standard already took into consideration these MCS rates, but again, they're not in the table yet. But the the 4 data rates that they added for NCS rates are 12, 13, 14, and 15. So the last two are for low bandwidth, high distance, IoT kind of solutions, or at least where the requirements for bandwidth are very low. So the modulation is one of the lowest ones, it's binary phase shift key, with a configuration code of 1/2, meaning of every 2 bits, 1 is a correction bit. So that's not going to give you very high bandwidth. Whereas the other two, 12 and 13, are going to give you the higher bandwidth. So this is one spatial stream at the shortest guard interval, where you can get at a 320 megahertz channel, again not in the EU, at 2.6 or 2.9 gigabits per second. Now if you calculate this with 2 spatial streams, 3, 4, 6, 8, 16, whatever, that's where those higher bandwidths are going to be. And depending on your modulation and coding rate, and especially the coding rate, either 3/4 or 5/6, again like this, 3/4 means 4 bits, 3 are data, 1 is correction bit, 5/6, 6 bits, 5 data, 1 correction bit, that's what that means. That's where you're going to see those high bandwidth. So these are the NCS rates that are going to be added into the standard. One thing that I'm not sure of, and I found this in different sites and different sources, but most likely is US only, but I did feel I need to share this, because who knows, maybe it'll find its way into the European community as well. It's called Enhanced QoS. What they have in the US apparently is, if you have a congested LTE network, and you have like a priority call, an emergency or whatever, and you are eligible to use that code for higher priority calls, you can request that priority, so a higher priority for your call, while suppressing the other ones. So it will give you a priority above all the others. They're thinking about something similar for Wi-Fi. So if you have a congested Wi-Fi network, but your client's phone or whatever has a feature that allows you to do this priority service, you're going to suppress all the other data and your client's going to get through first. I have no idea if you're going to see that, see this here. It might be interesting for like a hospital or whatever, where you have an emergency button where the network is congested, but you're still going to get through. Interesting. Not sure if they're going to get it, because this, for as far as I could find, is a US only thing. But I thought I should share it with you anyway. Those are the packed-in features that I could get my hands on, because the standard is not publicized yet. And some of the things already referred to a new standard called Wi-Fi 8, or at least they didn't say it's going to be called Wi-Fi 8, but logical thinking will be Wi-Fi 8 anyway. There's no .11 code for it yet.
It just got announced. Yes.
Oh, sorry. Missed that. What is it again?
PM.
PM. Oh, when was that? No.
A couple of days ago.
All right. I'm in between jobs at the moment, so I didn't look into it. So there's a new standard. Anyways, a couple of features in there, and I need to look in that. That drive Wi-Fi 8 already is, again, higher throughput, but even lower latency. Things like augmented reality, mixed reality, 16K video, automation, sensors, even looking at 60 gigahertz integration in the Wi-Fi standard, power consumption that needs to be optimized, and all that stuff. That's the idea for Wi-Fi 8. They didn't come up with that just by thinking of a list of interesting features. What they actually did is look at what the 3GPP standard is thinking of in their new 6G release. There's release 20 in 3GPP, similar to what IEEE does with the Wi-Fi standards 8 to 11. They've got the 3GPP releases, and they number those. And you see like a similar list of features that they're thinking of in 6G compared to what they're thinking of for Wi-Fi 8. So it's not that they just thought of something, there's a reason behind this. With regards to 6G, the expected release is going to be somewhere at the end of 2027. That seems like far away into the future, but it's getting closer really quick. And even 5G needs to be deployed largely at the moment. So that's 6G, so 3GPP is going faster and faster as well in their development. But again, same throughput requirements, same latency requirements, spatial efficiency, energy efficiency, it's all the same thing, just in another standard for LTE kind of solutions. So that's nothing new. Putting it all together shortly, even though 6G is coming, 5G is already here, but still needs to be deployed more and more, you see an enormous growth in Wi-Fi. I always get the question with every new Wi-Fi release, or no, let me put it differently, with every new 3GPP release, so with 4G, with 5G, and probably also with 6G, is this going to be the end of Wi-Fi? The reality is, since 4G, Wi-Fi has never been so enormously growing, and it keeps on growing. So no, it's not going to kill off Wi-Fi. Even so, if you look into the 3GPP standard, they actually refer to other access technologies to help them out to get to the promises, to make sure that they can commit to the promises they make for the 3G standard, or the 4, 5, 6G standard. So they need other access technologies in order to cope with the demand. So Wi-Fi is going to stay. Wi-Fi 7 is coming, Wi-Fi 8 is coming, client adoption always takes a bit longer. If I get the question, well, should I wait for the next standard? It's an eternal wait. So no, you should not wait. If you are looking at a refresh of your network at the moment, go for 6E. That's my advice. I typed this in and I got this. And actually, this is a small tech, and I'm not a hardcore Arjan van Buuren fan or whatever, but the text here, the lyrics are very close to what I believe for Wi-Fi. If I get everything that's happening in the Wi-Fi market with regards to all those new things that are happening, that's overwhelming, and it keeps overwhelming me more and more. But even so, if a new standard is there and it's certified and vendors are ready, clients are coming, go for it, use it. Because if you're going to wait, again, Wi-Fi 7 is going to be released next year, Wi-Fi 8 probably 2 to 3 years later, when are you going to change? When are you going to move into the next standard? So that's my advice. You should not wait, and I probably don't have time for questions. Or do we? Any questions?
Any questions?
I wonder about delay. What happened with one of the targets? 0.5 milliseconds delay.
Yeah.
Transfer delay.
Yeah.
Didn't address that.
No, I didn't address that because I simply don't know how they can accomplish that. Because it is a chipset delay most likely in order to process the data that's coming in. But you're depending on the spectrum availability. So the air needs to be clean, and if I'm having a collision or I have to wait for whatever I have to wait for, then my delay is going to rise. The only thing is the multi-link operation or even the distributed AP coordination might reduce that delay, but those are features that you need to adopt in your client in order to reach those low delays. We'll have to wait and see, like any standard. We have to wait until it hits the market to see if it actually works. Same with multi-user in 11AX or DMA in 11AX. The promise is great. The reality is you have to wait and see how it all works out. Yeah?
What is on the back side of the access points, you have some network cable and equipment attached to the other side of the cable.
Yeah.
Are they keeping up with all the speed?
They're gonna drop them.
Well, you see a lot of, basically if you swap out your switches nowadays, you've got multi-gig. So multi-gig is the way to go. All these APs will most likely have, or at least the higher end, have a multi-gig connection. But you have to keep in mind how this reflects into your entire network. Because if you got all these multi-gig access points on a switch that has a 1 gigabit fiber up to your data center, that's not going to help you that much. But again, it depends on, are you going to need the capacity, or is it just something that you have like a tick in the box in the RFP? Which is most likely to be the case, because I want to have the support for multi-gig and all that stuff. But the reality is you're going to end up with a lot of mixed clients for the upcoming years to come. Probably until I'm retired, which is in like 15 years or something, you're still going to have a mixed client environment. Meaning that your throughput is going to drop significantly, where the M gig and even the 1 gigabit per second threshold is hard to get by, to get over. 11AX, we've got a couple of networks on 11AX by now, a lot of networks actually. I have not seen one network that gets a throughput through the access point above 1 gigabit per second. And not that we're not supplying 1 gigabit per second, but if I reach half, then I'm doing my utmost best. 500 megabits per second, and you have to push it really hard to get that. Again, it's not the lab environment. In the lab environment, I can go crazy. I can get way above 1 gigabit per second. But in a real life environment, I'm never seeing anything like that. Again, those exceptions left out, of course, because there are always exceptions. Yeah. Thanks.